Hello everyone, welcome to the lecture of experiment 4 of CSE 350 lab. So in this experiment we'll mainly discuss about two types of digital to analog converter. So what we all know, digital signal, basically the signal which is discrete in amplitude, that means in time domain. It has finite, not continuous values in different time region, but analog signal, on the other hand, analog signal is a type of electric signal that has continuous values within a time period. So we know the computer cannot process digital analog signal. For this reason, we need to convert analog signal into a digital signal, and sometimes you also need to convert digital signal to analog signal. So which the component which converts the digital signal to analog signal is called a digital to analog converter, or DAC. So so in the all DAC basically works in the same format. They are actually use there is an op-amp which is used to convert the digital input signal to the continuous voltage level, and we can record this continuous voltage output from the output node, and then use it in other parts of the circuit. So in this experiment, we'll mainly discuss about two types of digital to analog converter. These two are binary weighted digital to analog converter, and RN2 are digital to analog converter. So let's jump in to the binary weighted digital to analog converter. You can see the circuit of binary weighted digital to analog converter in this slide. You can see it is basically digital to analog converter for four inputs. These four inputs are A, B, C, D. They are basically four voltage level indicator. We'll use when they are on, they are connected to a 5-volt voltage source, and we're connected to the ground. When they are logic low, that means you have a zero input. It is same for all four inputs here. Now we have all if you remember from the 250 we had op-amp part, which is not that much, but we in op-amp we discussed about in various types of op-amp circuit. One of the op-amp circuit was inverting summer, where multiple inputs are summed together. This is basically the same circuit. Here we have four inputs were inverting summed to the negative input of the op-amp, and positive input is connected to the ground. So if you remember the expression from that course, we can express the full summation or full summer in just this form, which is, you can see, this is minus 1 by 10 into VA plus minus 1 by 5 into VB plus minus 1 by 2, etc. So what are the significance of 10, 5, 2.5 and 1.25? These are basically these resistors, these four resistors connected to so we can they are also decreasing to the power of 2. We're dividing each resistor by half, and this is how the name binary weighted came. So we are actually in this similar way, we can also increase the number of inputs. For example, we can also add a 5 input or 6 input. Just we need to calculate the value of resistance and find the exact value of resistor for the desired output. We can also calculate the normal logic using the calculate the output value using the normal logic. Let's see, for example, our input A has a value of 1, and input B, C, and D has a logic level of 0. That means a 5-volt voltage source is connected to the input A. So we know there is no current flows into the inputs of the op-amp. That means this is connected to the ground, and so this will be connected to the ground too. So so for since logic A is value of high or 5, IA will have a value of 0.5 milliampere using Kirchhoff's law. This current can't be carried to the negative input, because we know no current flows through the inputs of the op-amp circuits or op-amp devices. So this current will flow using this region, and so the output will be basically the voltage across this RF is 0.5 milliampere into 1 k ohm, or 0.5 volt. And since we can say that VA using another, again using the different now VRF is equal to basically V0 minus V negative value, V this voltage minus this voltage VO. So we can say VOF equal to minus 0.5 volt only when logic A is high. In a similar way, we can calculate what happens when V is equal to 1 and A, C, D is equal to 0. In that case, it will be have a 5 value, and since this is connected to the ground, our IB will have a value of 1 milliampere. And other current IA, IC and ID will be 0. This 1 milliampere current will be connected to the through the RF resistor, and RF resistor will have a voltage drop of 1 volt. So the output will be minus 1 volt when only V is equal to 1 and ACD is equal to 0. Now if you look at the previous slide, we have A is equal to 1 and BCD is equal to 0. Here for our digital 4-bit input, basically A is the LSB and D is the MSB. So that means for our input of 0001, our output has a digital analog value of 0.5 volt. Now for us input of 0010, our output has an analog value of 1 volt. Now let's see what happens when A and B is equal to 1 and C and D is equal to 0. That means our A will have a logic value of high or 5 volt, and B will have a logic value of high or 5 volt. So IA will be 1 ampere, IA will be 0.5 milliampere and IB will be 1 milliampere. So their total current we can add using KCL node. We can see the total current will be 1.5 milliampere, and this 1.5 milliampere will flow through the RF resistor. So the feedback resistor will have a voltage drop of 1.5 volt. So our output will be minus 1.5 volt when A equal to 1 and B is equal to 1 and C equal to 0, D equal to 0. So for our digital input of a 0011, our analog output is minus 1.5 volt. In a similar, we can find the analog voltage level for all 16 possible combinations. So why 16? Because we have 4 input and 2 to the power 4 is equal to 16. So we can actually find the analog voltage level for 16 possible digital to digital combination. That is started from 0001 to 1111. So if we tabulate the output value, so if we tabulate the values using a graph where the x-axis has a digital inputs, basically 0001 to 0000 to 1111, that is 15. We can see the output has increased by 0.5 volt. So for a 0001, our output was 0.5 volt. For 0010, our output was minus 1 volt. For 0011, our output was a minus 1.5 volt. So it is actually increasing at a difference of 0.5 volt. This 0.5 volt is called a step. It means this step can be controlled. This step can be controlled using by changing the value of this RF resistor. So if I can manipulate the value if I want for example, if I want a larger step size, for example, it will be minus 1 volt to minus 2 volt to minus 3 volt. I need to modify this RF value using manual calculation, and I also can decrease this value. But one correction, we have to consider one condition when we are manipulating the step size. The output value must not cross the bias voltage level, which is 15 volt for our experiment. So you need to set the step value in such a way that our for any input, any digital input, our analog voltage level must be less than minus 15 volt.